Hello, can you hear me? Good morning. My name is Stefan Soroyu. I'm faculty at the University of Toronto in the Computer Science Department. University of Toronto is just a couple of blocks north of here. So unlike most of you who get to only spend about 3 days of winter in Toronto, I get to spend the entire winter every year. One good thing about research talks is that they're 15 minutes only, so hopefully they're going to be short and sweet, so I'm going to try to do that as well. Before I begin, I want to give you a little bit of a very high-level view of the research project that I'm doing. This is joint work with Troy Ronda, who is my graduate student. So what we're doing, we're trying to understand the prevalence of certain internet security attacks. In particular, how often people receive phishing emails and spam emails, and how often do people really click on the links in their emails? Why does this thing still happen, and why do people still fill forms online and buy Viagra and so forth? So to do that, we said we're going to trace the network traffic at the University of Toronto. Now, University of Toronto is a large school. It has 3 campuses. The campus downtown, which is the one here, if you go on University Avenue, you can see the campus is called the St. George campus, and it's the biggest. And there is a campus on the east side of the city, and there is a campus on the west side of the city. The one on the west is called University of Toronto, Mississauga. And we are tracing all the traffic going in and out of this campus, University of Toronto, Mississauga. So in this talk, I'm going to just tell you about what are some of the concerns that we had to deal with in order to protect the user's privacy when we trace network traffic. So just kind of to take a step back, about 8 months ago, we went to University of Toronto and we said to the ethics committee, and we said, we'd like to actually look at everyone's emails. And they said no. So it took us about 8 months to kind of convince them that we are going to offer some privacy guarantees. And the role of this talk is to tell you what we've learned, okay? Now, one thing I want to give a little bit of motivation. So a lot of people actually are doing network tracing. And today, in today's day and age, all this network tracing, in order to be interesting, you have to look at packet payloads. A lot of people talk about packet headers, collecting them, analyzing them, understanding what's going on. That's great, but all the good stuff and the interesting stuff, especially from a security standpoint, occurs in the packet payloads, not in the headers anymore. Now, the moment you start looking at packet payloads, now the privacy concerns escalates, right? Because you're looking at people's traffic. And typically, when you look at the research projects and how they deal with privacy, they pretty much all of them deal with what I call a 3-step process. Let's gather data, we're going to write it to the disk. Then offline, sometime later, we're going to anonymize it. And the way we're going to anonymize it is using a hash function. And there's a whole bunch of very smart hash functions. Some of them are what's called prefix preserving. In other words, if you have 2 IP addresses that share the first 2 octets, even after you anonymize them, the anonymized numbers, the hash values, are going to share the first 2 octets. And that's very nice. And finally, after we anonymize the entire data, we're going to throw away the raw data. And we're going to do an entire analysis on the anonymized traces. And because we like to actually disseminate our traces in the research community, we're going to post these traces online on a public website somewhere for people to download them and run their own studies, because that's very nice. We get a lot of citations that way. Okay? Now, the message of my talk today, if there is one thing I'd like you to remember, is that this 3-step process is completely inadequate from a privacy standpoint. You cannot go with a straight face in front of an ethics committee and say, oh, we're going to gather all the raw data and store it somewhere on the disk, and sometime in the future we're going to remember to erase it. That doesn't work, especially when you start talking to people, telling people you're going to look at their emails. Okay, so why is that? Now, for the next 2 slides, I'm going to give you a couple of attacks that can actually be mounted against your traces and can expose a lot of privacy. First of all, are what's called mapping attacks. Now, mapping attacks actually map from anonymized data back to the raw data. And there are 2 types of mapping attacks. There are known mapping attacks, and there are inferred mapping attacks. Now, what does it mean, known mapping attacks? So let's suppose you know that the president of the university's IP address doesn't share any prefix with no other IP address within the University of Toronto. Now, even if you've anonymized that IP address, looking into the anonymized trace, you can figure out the IP address of the president of the university, and that's bad. The second one are inferred mapping attacks. Inferred basically means you don't really have knowledge, but you can make educated guesses. So let me give you an example. If you look at the top 10 most popular URLs, okay, most popular websites in your trace, yes, they are anonymized, so you don't know what they are, but you can take some educated guesses. So for example, chances are google.com is one of them. okay? And then you can try to break the keys of the hashing functions that way. Let me give you a different interesting example. You look at peer-to-peer traffic, and you suddenly see that on November 3rd, 2006, suddenly there is this new file, which you've never seen before. You don't know the name because it's anonymized, but it's very, very popular. And then you look actually on IMDb, and you realize that this is the same date when the Borat movie is being released. And then you can say, I think I can take a pretty good guess as to what that file actually is, okay? And things like that. Third type of attack is data injection attacks. So an attacker knows that you're tracing, and it basically constructs traffic in a careful manner, and it tries to inject this traffic in your trace. Then it goes online, it downloads your trace, and it tries to look for those carefully constructed patterns in the hash trace, and it can learn a lot of things that way as well. There are also crypto attacks, plain old crypto attacks. Whenever you talk to a crypto guy, he'll tell you, oh, you remember the MD5 hash function? I can generate collisions in about 8 hours on my laptop really easily. And collisions are not particularly bad when you trace and when you anonymize things. The real question in my mind is, the moment you make these traces available, yes, they're going to be hard to be breakable from a crypto point of view today. But how are they going to be? Are they going to be able to be broken 20, 30 years from now very, very easily? Because if they are, people don't like to know that 20 years from now everybody can read their email. There are even more attacks, and on this slide I have what I consider are the worst attacks, the most worrisome. There are attacks on the tracing infrastructure. You have a machine that looks at all the traffic online and it has access to it. How do you know that that machine is not going to be remotely exploitable? Some guy somewhere is going to actually hack into your machine. There are also unanticipated attacks. We can just not be able to foresee the kind of attack somebody is going to be able to mount on these traces. And the example that I like to give, a couple of years ago, somebody showed that it's very easy to fingerprint the operating system of a host by looking at the timings of particular packets in the TCP streams. There's all kinds of clever ways to actually attack that you can really foresee so that you can protect yourself against them. And finally, the worst one in my mind is what I call legal complications. Some smart lawyer somewhere thinks that it's a good idea to get his hands on your trace, and it subpoenas you. And we're a publicly funded research group at a public institution. We have to, if you get subpoenaed, to actually give access to our tracing infrastructure. And if you have raw data on the tracing infrastructure, then that's particularly bad. And let me tell you why I'm really worried about this, is that all these attacks that I presented so far, if they could reveal some information, okay? But the one where you actually have access to the raw data, you reveal whole identities, actually, the entire full information of all the users whose traffic you're monitoring, and that's particularly bad. So we scratched our head and we said, okay, we learned two things. Here are two things we're not going to do. First of all, we're not going to write plain text or raw data to the disk, ever, okay? Because, like I said, you can actually, if somebody gets their hands on that data, you can get subpoenaed while you're running it and you haven't write it and you haven't erased it yet. And it's a very serious attack because it reveals full information about the identities of the people who you're tracing. And the second thing we actually learned and we decided not to do, we said we're not going to make these traces publicly available. We're not going to post them online. If there are other researchers that have interesting questions or studies or queries they would like to run our traces, we'll be happy to accommodate them. But we're not going to make these things available somewhere online so that people can download them and archive them and break them 30, 40 years from now or anything like that. Okay? So how are we doing these things? So I'm going to actually give you a picture here, kind of like a mental model of what we're doing. Now on this slide, you see three clouds. On the left, you see the internet cloud. In the middle, you have the main cloud, which is the St. George campus, the biggest campus at the University of Toronto. And on the right, you have the campus at Mississauga, which is the one we trace traffic to and from. There are two things I want to say on this slide. First of all, that Mississauga, the campus at Mississauga is connected to the internet via St. George, okay? So it doesn't have its own connection. And second, and the most important thing is that this picture is not up to scale. I'm not claiming here that University of Toronto is as big as the internet in terms of traffic or anything like that, okay? I'm just making these clouds big enough so that we understand what's going on. Of course, the internet is much, much bigger than the traffic we're looking on here. Okay, so what is it that we're doing? Well, we have a switch on the link from Mississauga to St. George, and it does port mirroring, and it has a one-way link into our tracing machine. Now, the dotted frame you see on the slide, that's one machine, and we basically split it into RAM or volatile memory and stable memory or stable storage. And that's one tracing machine, and we have a one-way link.
What does it mean to have a one-way link? Well, you take basically a fiber cable, which has an inbound and an outbound channel, and we only put the inbound channel into the machine, and we do not connect the outbound channel. In other words, we make sure that there is absolutely no wire or fiber optic cable or anything like that that can take packets and route them, send them outside of this machine. We basically disconnect our tracing machine from the internet. Because to my knowledge, this is the best way we can go in front of the ethics committee and tell them, we're pretty darn sure nobody's going to break remotely into this machine over the internet. There's no wire coming out of this machine. Okay? Okay, so what is it that we're doing? Well, we're getting packets on this one-way link, and we're basically doing everything in RAM. There is no kind of secret sauce here. It's kind of like bad news in some sense. So we're capturing the packets online, we're doing TCP reconstruction, HTTP reconstruction, we're doing more application level reconstruction. In particular, we're looking at Hotmail, mail that you actually receive with Hotmail and Gmail and things like that. We also run spam assassin in RAM, and we do everything in RAM, and then only after we're done, we anonymize the data, and then we write it to stable storage. Okay, so what does this mean? This has this nice property, which is if you unplug the machine from power, all that thing is gone because it's in volatile memory. So if you get subpoenaed and I've unplugged this machine from power, there is no raw data on this machine whatsoever. Okay, and you might wonder, how do you know there is really no raw data? What about the swap file, right? I mean, you can get, and we said, yeah, we're going to disable swap file. But the good news is, if you're tracing a line spins and if you start swapping things in and out of memory, you're probably too slow anyway and you lost, so you should crash rather than continue. Okay, so we're writing everything to stable storage. That's basically our answer, and that's how we're able after 8 months of discussions with the ethics committee to be approved to actually look at the people's webmail for phishing. So in summary, our infrastructure protects against intrusion attacks, and the way it does that is because it's disconnected from the internet. There is no traffic coming out of this machine. It protects against legal attacks to recover raw data, because all the raw data manipulation is done in volatile memory in RAM. And it protects against mapping, crypto, and anticipating data injection attacks, because we're not going to make these traces publicly available. However, the insight here is that some of these attacks, like the mapping, crypto, and anticipated attacks, are still possible if somebody gets their hand on the anonymized trace. One way to do that is to be subpoenaed. And we really don't know very well how to protect against that, other than saying that, even these anonymized traces, will make sure to permanently destroy them as quickly as we can. And that's our best answer so far. Now, this is my summary slide. I have one more it's kind of like the lamest slide in the whole talk. And this is kind of like some preliminary statistics about phishing. The reason why these are very, very preliminary is that we're basically tracing as we speak. Like I said, we do a lot of things in RAM. Our tracing infrastructure is really not rock solid. The longest trace we've collected so far is about 56 hours, okay? Because after that, we crashed because of all kinds of bugs and things like that. We do everything in RAM. So we're only tracing about 200 megabits per second. This was the traffic over the weekend coming in and out of this campus. We could probably trace up to about a gigabit per second with the machine we have so far. But this is a smaller campus, and it has only about 5,000 users. Now, we look at Hotmail for now only, and we've seen 200 people using Hotmail, and they have read, so this slide says received, but they have read, it's not received. They clicked on their emails about 700 times. So they've read about 700 unique messages, and about 3% of them are spam. Seems pretty low. The reason why it's low is because Hotmail does a fairly good job of filtering and classifying email as spam as well. So this is spam after that has escaped the Hotmail filters. Another statistic that I want to kind of finish with to that I found very interesting. This is again very preliminary, so I did not put this on the slide because take this with a grain of salt. Here's an interesting thing we found that I found very kind of counterintuitive. It turns out that if you look at clean emails that are not spam, many of them don't have links. That's great. But many of them do have links. And the interesting thing is that the number of links in clean emails is actually higher than the number of links in spam emails or phishing emails. And we believe that the reason of why this is true is because the bad guys really want to make you click on a single link. They don't want to give you too many links and options you can click on, because that's not good. They really want to click on this link, because if you click there, then good things happen to them and bad things happen to you.
And that's the end of my talk. This code that we're actually developing is going to be, and it is actually publicly available and open source and so forth, so you can actually download a copy and play with it. Thank you very much.
Thank you. Can we get the next presenter come up here while I ask if there are any questions?
Joel Yeagley. Just a quick observation. If you actually need disk or swap, it's pretty easy to generate a random key every time and have temp or swap file systems that are encrypted so that every time the machine reboots, you get new file systems. And it's actually quite convenient, and we use it in some collectors.
That's great. I actually looked at that also, and I think it's a good solution as well, and it could probably be done. The thing that I'm worried about what's being swapped and what's not being swapped. What if I want to make sure that the key that I have in RAM is not going to be swapped on disk ever? But you're right. I think it's a nice solution. I'm not saying absolutely, yeah.
Right. Well, I mean, if you want to talk to me about it later, I'm around.
Wonderful. Thank you.
Yes, sir.
Mike Hughes, Links. Thanks, Stefan. It was me who press-ganged him into doing this. Just another question was the machine that you're using at the moment. How much memory, physical RAM, and how much storage have you got on the back of that machine?
So we have only 4 gig of RAM. And here's one thing I kind of learned doing this is that, having more RAM is nice. There is nothing wrong with it. But the reason why you're running out of RAM is because you probably have a memory leak somewhere. And if you have 8 gig instead of 4 gig, or 12 gig instead of 4 gig, rather than tracing for 3 days, you're going to be tracing for 5 days or something like that. So we're better off trying to go after that bug and try to fix it.
Yeah, that's quite a useful point, because I know, we've been doing some work with things like SFlow data, and one of the things that we have is trying to handle this much stuff, and you're almost doing things in RAM disk and then having to commit stuff later, and so that you can actually make the thing fast enough, because you've got so many Mac-to-Mac pairs, for example, in my application. But that's really
But
useful
you're
stuff.
right. The biggest bottleneck we have is RAM, and the second biggest bottleneck is CPU. Storage is not really an issue.
Yeah. Okay.
Thank you.
Thank you very much.